Next we have Lenny, and Lenny's also from Juniper Network. So we got a Juniper start here in the morning. He'll be talking about tree-based CDN for live streaming. If live streaming is something you're interested in and traffic is your concern, then this talk is probably for you. Over to you, Lenny. Thanks.
Great. And can you see my slide? Do you see the correct screen?
Yes, we can.
Great. Well, thank you for having me. My name is Lenny Giuliano, and today I'm going to talk about TreeDN, which is a tree-based CDN architecture optimized for live streaming to mass audiences. So before I begin my talk, 3 quick questions that are going to be kind of the focus of the talk today. First, are we approaching an inflection point for network resources that are being consumed by live streaming? If not now, will we ever? And if the answer to either of those questions is yes, what should we do about it? So first, let's look at live streaming by the numbers. A high def bit rate is about 5 megs. 4K bit rate, the numbers I've seen are 35 to 45 megs per stream. 8K is about double that. And AR, the bit rate on that is, the numbers kind of are all over the place, but fairly astronomical, from a half a gig to 5.2, a whopping 5.2 gigabits per second. Akamai is one of the biggest CDNs, if not the biggest. And every year they announce that they break their own record for the most amount of traffic that they send simultaneously over the internet. The last one I noticed was they mentioned it was 167 terabits. If you just divided that by 40 megs, just to see how many simultaneous 4K viewers that would be, that would come to 4.2 million simultaneous viewers. And that's all it would take to set a new traffic record. To give you a sense of, what that looks like, that would be the 117th most popular show on television. So that's all it would take, is the 117th most popular show on television. If everyone watched it at 4K over the internet, that would break that record that Akamai had announced. But it goes up from there. So up until now, the way live streams are handled, or streaming in general is handled, is you can think of it as brute force unicast. If you have 10 viewers, you send 10 separate streams. If you have 10 million viewers, you send 10 million separate streams. If we just, and we can think of this as brute force unicast, and can it continue to keep up? To give you an idea, that the average television audience, or for an NFL game, that's American football, is about 15 million viewers in the game, not a marquee matchup. If you just multiply 15 million viewers by 40 megs, that would give you 600 terabits, which is about 5x larger than that record that we mentioned. And this year, the latest television deal for the American football includes games that will be exclusively available through streaming. Basically, you'll only be able to get them by watching through Amazon Prime. Other major events kind of go up from there. The Super Bowl, which is kind of the championship of American football, has over 100 million viewers typically each year. It's 2 to 3 times that for Cricket World Cup, and the last World Cup finals in soccer or football is non-American football, would be 500 million simultaneous viewers. And then the other thing to keep in mind is that the cord cutting evolution, which began really the maybe 12 to 15 years ago, with things like Netflix and YouTube and Hulu, was really all about on demand. But live linear TV is kind of the last frontier. It's like the last thing that's keeping people from that is still keeping those holdouts from cutting the cord. And if you look, you see things like YouTube TV, Sling TV, Hulu TV. That's where a lot of the energy and excitement is really about. It's about capturing those that last group of people who won't cut the cord because, you know, they want to watch sporting events. And you know, the key thing to keep in mind is live linear TV is not dead yet. And in fact, it's actually trending. So we live in a fake world of fake news and deep fakes and, you know, a low trust world where, you know, the typical corporate communications of your typical large company looks like it had been written, you know, stolen from the pages of Orwell. As a result, you know, because live streams are, you know, by their nature, spontaneous and uneditable, they're perceived as more authentic and emotionally engaging than on demand. And marketers have known this. People spend more time on live video. The ROI is much better with live streams than any other social media or on demand. And then, you know, the pandemic kind of pushed the need for solutions that allow people to gather virtually simultaneously. Things like e-learning, fitness, wellness, you know, sporting events, worship services, conferences like this. And the numbers kind of bear it out. You know, the numbers in the first few months of the pandemic, live stream events just exploded by, you know, 1,500%. Watch time increased, you know, by 250%. And in China, live streaming e-commerce is absolutely exploding. So the conclusion here is live linear video is here to stay, but IP unicast, which is the predominant method of delivery over the internet, is well suited for just about everything except multi-destination traffic. This is indeed why multicast was created several decades ago to solve this very problem, but it really didn't. So what went wrong? And when I say it didn't, I'm really referring to internet multicast. You know, multicast itself has been deployed widely on things like financial networks and video distribution networks, enterprise networks, VPN networks. But those are really walled garden deployments. You know, what I'm going to talk about here is true over-the-top interdomain internet-based multicast. And that has not had a very good story. So let's look at why. So in order to understand why, let's go back to the beginning. In the beginning, there was unicast, and if you had an interested receiver, they would get a stream, and if you have multiple receivers, they get multiple streams. And you can see this gets costly at the source. You need a server big enough to handle all these streams, and you need enough bandwidth to support each of these streams. So that's why multicast was created. And the way multicast works is it builds a tree. It dynamically and intelligently determines who are interested receivers, builds a tree to those interested receivers, and sends traffic only to those receivers in such a way that no link carries greater than one copy of the data stream. But there's a problem with multicast. The internet is not a monolithic network. It's actually a network of networks. And some are multicast enabled, but most aren't. So if you have a multicast enabled source on a multicast enabled network, but you have a unicast only receiver, the result is unbounded sadness. Sadness on the part of the receiver, who is not able to access content, and sadness on the part of the source, who has multicast content, is on a multicast enabled network, but and has an interested receiver, but that receiver can't access that content. This is known as the all or nothing problem. And what this means is every single layer 3 hop from source to receiver must be multicast enabled in order for it to work. That means every single router, firewall, every interface needs to be running a multicast enabled, a multicast routing protocol like PIM or MLDP. Otherwise, it won't work. So what do? CDNs were invented and became very popular. There's different models for CDNs, but one of the more common ones is, you have that same source who sends the stream to a CDN box, and a bunch of CDN boxes are deployed throughout the network. And content is sent to one and it gets pushed out to the rest, and they handle local receivers. It's almost as good as multicast, and it just works. You don't need every single router and firewall to run a bunch of a bunch of new protocols. So if we compare unicast, CDNs, and multicast, if we just look at cost as a function of audience from the perspective of the content provider, and that's important, it's got to be from the, if we look at this from the perspective of the content provider, what we see is with unicast, it's simple, simple linear. You have 10 viewers, you send 10 streams. You have 10,000 viewers, you send 10,000 streams. CDNs still have a per viewer cost, but the slope of that line is much smaller. That per user cost is it's much more efficient, and that per user cost is much lower. But do notice that there is an initial cost to deploy CDNs, and that is you have to get those CDN boxes, rack them, stack them, plug them in, power them up, and plug them into routers, and burn up router interfaces. By comparison, multicast, whether you have one viewer or a million viewers, the cost to the content provider is constant. So the marginal cost for each additional viewer is zero to the content provider. So one thing to keep in mind with this is CDNs don't eliminate the brute force unicast problem, they just distribute it. One example is UMetSat, which is an organization in Europe that does basically atmospheric monitoring with weather satellites, and they stream atmospheric and weather telemetry data, large use multicast, interdomain multicast. They're probably the best example of an interdomain multicast content provider. They have said that, I asked them, what about, why not just use unicast CDNs instead? And they said unicast CDNs would be an order of magnitude more expensive than what we're doing with multicast. By the way, just because as a technological aside, that all or nothing problem, V6 has the same exact problem. I think V6 and multicast are kind of related. I'd call them technological cousins, in that any argument for or against V6 applies equally well to internet multicast. There are folks who say, we don't need V6, we've got NAT. Same thing goes for multicast. We don't need multicast, we've got CDNs. On the other hand, the advocates would say, absolutely, we need V6. We have this V4 address exhaustion problem. Likewise, on the multicast side, there are folks who would say, all these duplicated video streams is incredibly inefficient. It's an incredible waste of resources on the network. Both suffer that all or nothing problem that I mentioned. Both require new protocols or extensions of old ones. Both were born around the same time in the, kind of in the 90s. They struggled through adolescence. And while, V6 is doing much better than its cousin multicast, it's still kind of unemployed / underemployed, with, they're both kind of still living at home with their parents, who are a little nervous about the failure to launch. V6 is certainly doing better these days, but after about 30 years, it's still at what, say 20%. Depends on how you measure V6 adoption. But both also require faith in the unseen, in that little can be accomplished on their own, but these enable bigger things. You don't just turn on V6 or multicast and just magic happens. They really are they're infrastructural enablers of bigger things that take advantage of these infrastructures. So what's new? Internet multicast, like I said, it's been around since the 90s, hasn't gained much traction. Why should this time be any different? Well, let's examine the three problems of internet multicast and why it didn't take off. and see if, has anything changed. So first is the all or nothing problem that I mentioned. Second is the second biggest problem with multicast is it's too complex, and operators have been complaining since the dawn of multicast that too complex to understand, to manage. It's a bunch of protocols, really difficult to troubleshoot and figure out what's going on. There's also this content audience chicken and egg problem where there's no content because there's no audience, and there's no audience because there's no content. So there are some new things to keep in mind. First is ASM deprecation. RFC 8815 is a BCP level recommendation to stop using ASM. It turns out multicast is not complex. It's ASM that's too complex. It's more specifically network-based source discovery. We would never ask unicast to discover sources, yet we do that with multicast. And it turns out that is the root of the vast majority of the complexity. If you just move to SSM, source-specific multicast, move source discovery to the application layer, you can eliminate about 90+% of the complexity of multicast. Multicast, suddenly you no longer need rendezvous points, MSDP. You no longer need shared trees, SPT switchover. There's no more PIM registers or NCAP or DCAP. All those weird corner cases of PIM go away when you use SSM. And so that solves problem number 2. And then overlay networking. So when I started in this business, tunneling was seen as a suboptimal hack to be avoided. Turns out if you just rename it overlay networking, all the cool kids are doing it. Suddenly, tunneling has become fashionable just by calling it overlay networking. We're essentially taking advantage of that trend with a technology called AMT, automatic multicast tunneling, which I'm going to explain in a moment. Automatic multicast tunneling essentially allows you to tunnel over the parts of the network that do not support multicast. So it allows multicast to work where it works, and you don't have that all or nothing problem. It also, by the way, solves the chicken and egg problem, where all of a sudden now the entire internet becomes an available and potential audience. So all the pieces are in place for a workable solution today, and that's key. And I'm going to talk about that. So first, let me describe AMT. What is it? How it works? So imagine you have a multicast enabled service provider. There aren't many of them, but they do exist. The research and education networks are the primary examples. Giant, which is the main RNE network in Europe, is one example. And imagine you have a multicast enabled content owner. Again, there's not many of them, but they do exist, like UMETSAT. And then imagine you have a multicast enabled local provider. Again, not a lot of those, but they do exist. Think the RENs that might connect to the Giant network. So you have a bunch of interested receivers. They receive multicast natively, the way we all understand multicast to work. That's great. But what about the more common scenario of 99+% of the internet, which is unicast only? You have an interested receiver who sends an IGMP report to their last hop router, but that last hop router doesn't support multicast, so it just gets dropped. However, if this receiver has a thing called an AMT gateway, which is a thin client that is able to build tunnels to a thing called an AMT relay, which is a box that sits at the border of the multicast enabled network. And so this the gateway magically discovers its nearest relay and sends, basically builds a UDP tunnel dynamically, sends an IGMP report through that UDP tunnel. The relay then treats it like a local receiver, turns it into, say, a PIM join, receives the traffic natively, and then sends it back through the tunnel. And as you have more and more interested receivers, they create separate AMT tunnels. And now we see, by the way, those unicast only networks that previously had no really good reason, no business case to turn on multicast, because why bother? Nobody's using it. Well, if all of a sudden they're carrying a bunch of duplicated unicast streams, they finally have a reason to turn on multicast. So you can think of AMT as a kind of a temporary stopover. It's not a permanent destination. It's really a motivator to get multicast to work, to benefit the content providers and the multicast enabled networks out there, and tunnel over the networks that don't, and essentially give them an incentive to turn multicast on natively. So you might say to yourself, gee, that looks an awful lot like a CDN. And let's look at that. So you have these, CDN. Let's go back to the original picture of what do CDNs look like without multicast. You send content to each of these CDN boxes who handle local receivers. That's how it works today without multicast. What would it look like with multicast? Well, first, those CDN boxes, we'll rename them. We'll call them AMT relays. And we'll move them closer to the receivers, so they're at the true edge of the network. You can send a multicast stream only to the relays that have interested receivers connected near them, and then they use AMT to tunnel that traffic. So it kind of looks similar, but there are some interesting side benefits. First, the replication point is closer to the receivers, and the traffic only goes to relays with interested receivers nearby. Second, these relays don't need to be boxes that need to get racked and stacked and plugged and powered and plugged into routers. If you have routers at the border of your network that support AMT, essentially you can offer this as a replication as a service or CDN on a chip for zero capex. For example, there are routers out there that all it takes is 4 lines of config and they become AMT relays. There's no additional hardware, no services blades, no special licenses. The Juniper MX routers are one example. There are other vendors who support it. I believe Cisco does support AMT as well. So without deploying these special CDN boxes, plugging them in, powering them up, plugging them into routers, and racking them, you could offer, an operator could offer this replication as a service for essentially zero capex, and you could even argue zero opex, because there's no, it's an inline feature that doesn't require any additional power or resources. So rather than just talk about this in PowerPoint slides and say, look, wouldn't this be great? We decided to actually build a TreeDN network. Like all great plans, it took.
Sorry for the interruption. 4 more minutes to go for the talk. Sure,
gotcha. We decided to build this architecture in all great plans require 5 steps. 5th step, of course, being profit. So let's talk about how we got there. So the first thing we did was deployed some AMT relays. Today, there are 4 public relays. The first one was deployed, and they're all connected to currently to Internet 2, which is the RNE network in the US, in North America. We'd love to have more. If there are anybody who wants to be part of this TreeDN network and wants to deploy an AMT relay, we'd love to have you. We handle relay discovery through DNS and let the application layer essentially receive an ordered list of multiple A records, each corresponding to one of the 4 for all 4 relays, and the application layer picks one, and kind of, if it doesn't receive packets, it goes through the next one. So you get redundancy, reliability, and load balancing, though not optimality, with this scheme. The next thing was building gateway implementations. It turns out, there weren't any gateway implementations at the time after we started deploying these relays. So the goal was to build this in the browser, but the browsers are pretty locked down today. They don't even support UDP. If you can't get UDP, you can't get multicast to work. So basically, VLC was chosen to deploy. We had a couple engineers at Juniper, Natalie Landsberg and Wayne Brosum, implement AMT Gateway and VLC, and that is part of VLC code that you can download today. By the way, Akamai is leading the work at IETF and W3C to support multicast to the browser. The next thing was a content portal. How do you find content? I would encourage everybody, check this out. You can actually see this stuff all working. And this was developed by a high school student named Lauren Delwich at Thomas Jefferson High School. And it discovers multicast streams, puts them on a web page, so you can click it and that'll launch VLC with AMT. So you can actually access multicast content and see it all working. And the last thing is off-net sourcing, which would allow you to source content with, say, a smartphone and send a unicast stream to a translator that would turn it into a multicast stream, and then it could be received. So if you kind of put all these things, and this was demonstrated at IETF 112, click on these links, you can see some of this. So putting it all together, here's the Big I Internet, that's mostly unicast enabled. Here's the MBone, the multicast enabled part of it. You have a native source, native receiver that works the way multicast has always worked. You have an off-net receiver, unicast only receiver. The traffic is sent to the relays natively and tunneled via AMT. If you have a unicast only source, they send to the unicast stream to a translator, which turns it into multicast and delivers it natively or via AMT. What's in it for operators? Well, going back to my original questions, with exploding live audience sizes plus increasing bit rates, maybe time for a new approach for CDNs. Creates a viable business model for live streaming to mass audiences. You can offer replication as a service at a fraction of the cost of CDN only, unicast only CDNs. And is it healthy that for the internet and society that only a handful of companies control nearly all content distribution? This gets us back to decentralized content sourcing. Here are the references. And I don't know if we have any time for this, but for questions, but I'd be happy to answer any questions with any time available, or just please reach out to me.
Thanks. We are almost out of time, but I think we can squeeze in one question. I see one raise of hand from Rahul. Rahul, can you unmute yourself and ask your question?
Yeah, sure. Hi, Lenny. My question is, so disclaimer first, my knowledge is quite limited when it comes to multicast delivery, but still what I've learned so far is SRT works on the same lines. So if you could shed some light on how is this different, like what is the difference between AMT and SRT?
SRT, remind me what that stands for. I'm less familiar with that. What is SRT?
So that's a protocol basically which works as per my knowledge exactly the same. There might be some differences. What I was keen to learn, like what are the differences? So to bridge the gap, from one multicast enabled network to the another multicast network, transporting the stream over a unicast only network. So that's exactly what you have shared with us. So that's what made me curious, like how and what are the differences.
What does SRT stand for?
I'll need to look it up though.
Okay. Yeah, sorry, I'm just not familiar with that. I can tell you that, I've been pretty engaged. I'm working group chair at MBOND at IETF, and I've been attending, the various protocol, like PIM working group. Never heard of SRT, so I'm not sure if that's what that is or how that works, but
SRT stands for Secure Reliable Transport.
No, I think from a multicast perspective, Srinath here, it is actually source routed trees. Okay, so that was one of an earlier draft in IETF a long time ago, but I think it's some implementations exist, but not widely used. That's my understanding.
So quick Google search says Secure Reliable Transport is a royalty-free open source video transport protocol that supports low latency, high performance streaming over noisy or unpredictable networks such as public internet. So and in my experience, what I've learned from the experts in the industry, they have suggested me to use SRT to transport multicast traffic over the public internet or unicast network in general. So
yeah, I guess I can't. I don't have a good answer for you. I've never, I can tell you, having been attending IETF meetings and working with lots of customers, I've never heard of SRT or you know, there were originally a number of different proposals for tunneling multicast dynamically, and AMT was the solution that was arrived at through collaboration with a number of vendors, Cisco, Juniper, Microsoft, and a number of other folks, all really collaborating and working together. So, you know, for tunneling of multicast over unicast networks, and really AMT is focused on tunneling to the end. It was really designed for last mile.
Yeah, that too.
Tunnel to end
And I read on the Wikipedia page for there is a SRT alliance with a well-known members of Wowzer Streamings, if you know of them. They are doing quite well in the unicast delivery.
Rahul, maybe in the interest of time, you can take it offline.
Yeah, no, yeah, thank you.
Yeah, I'll be happy to take a look, but I can tell you, for when it comes to multicast tunneling to you know, of multicast streams to unicast receivers, AMT is the predominant technology.
Thank you. Thank you.
Great, thanks.
Thanks, Lenny. Thanks for your presentation.